So thank you everybody for tuning back in to another week of the Scientific Machine Learning webinar series or course, as Karthik was just referencing. I would just like to take a second to introduce myself since I'm new here. My name is Emil Annevalank. I'm a new postdoc in Professor Viswanathan's group, working on scientific machine learning as well. And I'm stepping in for this subsection on statistical or machine learning and information theory, because Dilip is preparing for his defense next Monday. So today I'm excited to listen to a talk from Pratik Chaudhary from the University of Pennsylvania. And this talk is the second in our series on the intersection of information theory and machine learning, which was kicked off last week by Alex Lemmy. If you missed that talk, you can find it through our website. And we have links to the recording from each seminar there. So without further ado, as people who are familiar with this webinar series, I'd like to introduce the session chair for today, who will be moderating Pratik's talk and the subsequent discussion. So our session chair for today is Professor Karthik Durasamy from the University of Michigan, where he runs the Computational Aerosciences Laboratory. Professor Durasamy is an expert in data-enabled physical modeling of systems with applications from rocket engines and high-speed air vehicles to trajectory optimization and control algorithm. And recently, that is also starting to include information theory and machine learning, which makes him a natural fit for this webinar series. So I look forward to the expertise that you will bring to this session, and please join me in welcoming Professor Durasamy as the session chair.
Pleased to be here. And again, without even further ado, let me introduce our speaker. Our speaker is Professor Pratik Chaudhary from Electrical Systems Engineering and Computer and Information Science at UPenn. He's also a member of the well-known GRASP laboratory. So Pratik got his bachelor's degree in 2010 from IIT Bombay. And then he went to MIT, where he got his master's and engineer's degrees in aeronautics and astronautics. And after that, he went to UCLA, where he did his PhD. And as we were discussing earlier, as one of the outputs of his PhD, he produced a very nice paper and a series of good talks on the connection between stochastic gradient descent and how it connects to variational inference. From 2018 to 2019, he was senior applied scientist at Amazon Web Services, and also he was a postdoctoral scholar in Caltech. And yes, so he joined UPenn, I think, in 2019.
Yeah.
Right? That's not on your bio, but I'm assuming.
Yeah.
All right.
Yeah.
So yeah, we are pretty excited for this talk, and it's titled Towards the Foundations of Small Data, where he's basically bringing information theoretic algorithms and seeing how it can be used to interpret and define transfer learning. All right, Pratik, over to you.
Cool. So thank you for a very kind introduction. This is an exciting series, so very, very happy to be here. Thank you for inviting. These are topics that are very near and dear to my heart. So it's always fun to think about them. The title of this talk is a little ambitious. So foundations of small data. So I've added like a towards the foundations of small data at the top, with the idea that maybe in a few years, this stuff in the brackets will disappear and we will get something out of this. This is a program. This is a series of 2 or 3 papers that I will talk around. And the goal is as follows. So stuff that we'll do today. So I'll tell you a little bit about what is called few shot image classification. This is a new problem, kind of became popular a few years ago. Very interesting to think about from a statistical perspective. This has motivated a lot of stuff that I will talk about today. In particular on transfer learning, and we'll look at some information theoretic ways of understanding transfer. And we'll also kind of look at some no free lunch style results, that I like to call them, of when transfer learning does not work or should not work, and what you should do if it does not work. Okay. So here is how I perceive the literature. There is, roughly speaking, three regimes of image classification. Let us focus on a very simple problem of classification. Roughly speaking, if you give me 100 to 1000 samples for every class, we are good at training neural networks today. So stuff that is frequently occurring on the internet, cars, cats, dogs, planes, you can pull up the usual bag of tricks and design good machine learning models for this. We may not know very well why they work so nicely, but it is true that they do work. The second regime, which is becoming interesting, is when you don't have these many samples, when you have, let's say, order 1 samples, maybe not more than 10. And this is what people call the low shot regime or the few shot regime. And the fundamental problem here is that imagine that you are Google or Amazon or something, and a farmer in Illinois, he grows strawberries on his farm, and he would like to build a classifier to classify this data. Of course, he doesn't really know machine learning too much. And if you tell him to sit and annotate 1000 images for his produce, he's not going to like you. So he gives you 10 images and say, okay, do something that you can and give me a classifier for this kind of data. And what do you have to build such a system? Well, you have all the data from the frequently occurring categories. And the hope is that you can transfer some of these models to this new regime and build these models quickly. So this is why AutoML style ideas are taking root. But this is the fundamental problem of reducing the amount of data that you need and tackling new categories. You don't have to stop here. So you can think of extreme low shot regime, which really looks like anomaly detection today, but it's a little different than that. So imagine a robot that travels around in the Amazon rainforest, and it discovers new objects that it definitely may not have seen before, but maybe we haven't seen these species at all. So the ability to recognize when an object is new is something that we haven't even thought about today. So as far as the universe, as far as the ImageNet model is concerned, the universe is partitioned into 1000 categories, and that's it. So this is where we would like to go towards if we want systems that can evolve, systems that can live in the physical world and do a good job of such world. Okay, but today I'll be talking about this regime essentially. How well do current methods work? So this is a plot that I like to show of some few short learning algorithms. There are many others. These are the ones that I put on this plot. And on the y-axis is what is called the one-shot 5-way accuracy. So one-shot meaning I give you one labeled image. 5-way meaning I give you 5 new classes, so 5 different kinds of strawberries, and you have access to inordinate amounts of pre-training data from other classes. So this is kind of a challenging problem, right? Because there are many, many different 5 classes that I can ask you to solve, and you may not do well on all of them. And that is indeed what you will see. So this is a box plot. So the horizontal line is a mean, and these are 99% of the distribution of the accuracies. And you will see that it has such a large error, and that's not really specific to a particular algorithm. Every algorithm has pretty huge error bars. And the reason I am showing this plot is for you to appreciate that tackling new tasks, tackling new classes is fundamentally difficult. The universe has millions and millions of different categories. And even if you only evaluate yourself on distinguishing between 5 of them at one go, there is still so many diverse episodes that you will not do well on all and choose 5 tasks. And the moral of this literature is that while we've been busy comparing the mean accuracy of these algorithms, no one really noticed that the standard deviation is so large for all these algorithms. Here is how some of these methods work. you know that you are not going to be tested on the same objects that you train on. So you don't really care about classifying them. What you care about more is learning how to cluster them. So think of learning a clustering model on your training set, not a classification model. So its object, it is measured, the merit of this model is measured by how well it can cluster features from the same class. And now given a new class, let's say I give you three-way classification, so three different classes. You plug in these images of every one of your label data. So I've in the picture in the previous slide, we were giving you one labeled image. So every one of these little circles will be, there will be only one circle like this. This is called the support set. And using this support set, you will be able to understand what the means of the clusters are in the feature space, roughly speaking. And given a new data point from one of these 5 classes, or one of these 3 classes in this case, you will be able to check the affinities and classify it depending on which cluster it lies closest to. So this is, in a nutshell, how most algorithms for few-shot learning work. Here is a slightly different take on the same problem. And that goes as follows. So a classifier at the end of the day is a function f that we like to use to predict on data x. So y hat are the labels, x is the input data. And how do you pick at this function? Well, I give you a training set, and you, of all possible functions that you can potentially pick, you pick the one that does well on the training set. So the function that you picked is a function of the training set and the test datum. Now, no one is stopping you from searching the entire function space at test time and picking the right, picking the best prediction. Of course, you don't want to do this because it is slow, and that is why you come up with this concept of a statistic or weights or parameters, which are really a function of your training set that simplifies your job at test time. So you don't have to search over all these functions. Okay, so basics of how we would think of machine learning. Now, the problem with few-shot learning is that you don't have too many samples. So remember that I gave you 5 new classes, but I only gave you 1 label datum for each class. So you don't know very well how to search over this set of functions. If you try to learn a weight vector using this 1 label sample, you're not going to do a very good job. You will have a very high variance in the predictions, for instance. So here is one trick, and this is what is called transductive fine-tuning. It's conceptually very simple. You have your training set, the frequently occurring cars and cats and dogs of images of all these categories, and let us call them NS. I give you few new images from the new classes, let us call them NT, and I would like to optimize an objective of the following form. So I'm going to find weights W that not only work for the entire training set, but they also work for the entire test set. Now, of course, you don't really know the labels of the test set, so it doesn't make sense to have it in this function. But well, you can use only the input images of the training set. You don't have to use the label. So think of it as some kind of semi-supervised learning approach where there is supervision occurring on the training set and unlabeled data from the test set. And the key idea here is that if I force you to predict on 1 test image, then you will have a very hard time picking a particular weight vector. But if I give you 10 test images, maybe you can learn some notion of similarities between their inputs, forget the labels, and do a better job of solving this minimization problem. So transduction is an old idea. Vapnik discovered it in the mid-90s. And the fundamental idea here is that instead of making prediction on 1 test datum at test time, that is what is called inductive reasoning, you make predictions on multiple test data at test time using some notion of semi-supervised learning. In a picture, it looks like this. So this is a classical cartoon of an SVM, of a max margin SVM. This is a positive class, it's a negative class. You would pick a hyperplane that splits them cleanly and nicely. Now, if I give you, so these 2 point clouds are exactly the same, except that I've shown you a few unlabeled test data. Now, given this unlabeled test data, you would imagine that the hyperplane that was like this, separating your training data, you can imagine modifying that hyperplane to do a little better job of splitting these test data. And this is, in a nutshell, how transductive learning works. In a picture, it looks like this. So this is a slightly complicated picture, so follow me here. There are 5 new classes that we are showing to the model after it was trained on. The big crosses are the labeled images of the 5 new classes on using the pre-trained network on the frequently occurring classes. Okay, so this is the feature space and this is the TSNE of the feature space. And this is where these are all the labeled samples that I gave you before you wanted to do few shot learning. These translucent circles are all the unlabeled features or the features of all the unlabeled test images that I wanted to make predictions upon. Now, given these point clouds, it's very unclear as to which points lie close to which clusters. I've colored them by their true class, but of course you don't know it a priori. And given such a cluster like this, it would be very hard to design any kind of Gaussian mixture model affinity to split them into their correct classes. So the green points should belong to green, but then of course you don't really know how to split this cloud cleanly. What transduction does, or what explicit fine tuning does, is that it takes all these translucent features of the test images and reduces their entropy, reduces the entropy of the predictions. So it forces them to go closer to one of these clusters. And as you can see, the purple test data points migrate towards the purple support vector or the purple label sample, which also moves a tiny bit. And you will still make mistakes. So for instance, this blue point should really have been here, but it has migrated towards the purple point. So you will, of course, make mistakes because you are using, you are forcing only the entropy to be small in predictions. But this is much better than clustering this kind of a feature space a priori. And one thing that is often missed in these kinds of problems on metric learning or few-shot learning is that the features of neural networks always look like this disentangled mess. They're not these clean Gaussian clusters that you would imagine checking affinities on easily. But for well-trained classifiers, the ones that get you good accuracies, the feature space looks very messy like this. It's not very easy to cluster, no matter how high up the layers you go. Okay, I will not belabor this table. These are just some accuracies. The important point is not the bold numbers, but rather the diversity of existing algorithms. So let's say in the last 5 years, there is thousands of papers on this topic, and people will come up with complicated tricks to solve few-shot learning. But just fine-tuning works better than essentially everything out there if you implement it well enough. And this is really the simplest possible method you can think about for doing few-shot learning. Pre-train a classifier on the training set, fine-tune it on the few labeled samples that you get. And this is what started me on understanding transfer fundamentally. If transfer works so well, then there is clearly something very powerful we can do with it. And here is one example. So this is a large data set. This is the big cousin version of ImageNet, 21,800 classes, 14 million images. And it's a very difficult data set for the following reason. So these are classes on the x-axis, images per class on the y-axis. And for the frequent classes, there is about 3,000 images per class. But then you'll also find classes in this data set which have 10 images or even 1, for instance. And this data set has a lot of mistakes in how it was annotated. Lots of images have multiple categories, etc., etc. The ImageNet that you and I use every day, very often, is the stuff in the blue region. So in this experiment, we took data from the blue region to pre-train a classifier, so frequently occurring categories. And we took data from the green region. There is about 13,000 classes in the green region. And we are picking 40 different classes, a subset of these 13,000 classes, or 20 different classes of these 13,000 classes, and evaluating how a pre-trained classifier on the blue region does on these new classes. And this is quite dramatic. So in the previous table, you were looking at accuracies of roughly 70% or so with one labeled image per datum, per class. Because the training set is so rich now, you're getting accuracies as high as 90%. And with a few more practical tricks, these algorithms are essentially good enough to be deployed in practice. And the moral of this story is that simple methods work. And the beauty is that beauty of such methods is that you can also implement them at scale. The diversity of data in ImageNet 21K is so large that the blue region gives you essentially all the nice features to use to classify the green region, even if the categories themselves are different. And this is kind of my perspective coming into transfer. I would really like to understand why is it that transfer works so well, and why is it that all the other methods. So it's not that there is nothing sophisticated going on here. These are very complicated methods with good ideas, but transfer essentially works as well as them, even better in most cases. And here is one way to understand transfer. So this is what is called the information bottleneck principle. It is a generalization of what is called rate distortion theory in information theory, and it goes as follows. So if you have data X and you would like to make predictions on some classes Y, so X and Y are random variables, at the end of the day, you want to learn a representation of the input image. Think of it as the features. You can also think of it as the weights of the pre-trained network. Doesn't really change anything in what we will say. But this representation of the input data is what you want to learn. And how should it be? Well, it should be sufficient to predict the targets Y, and sufficient means that it should be good enough to make accurate predictions on target Y. You would also like this representation to be small in size, so you can write it down on your hard disk. And one way of measuring how small the representation is the number of bits. So the size of your zip file when you zip a particular folder is a good measure of how much information that folder consists of. And Tishby in the late 90s started playing around with functionals of this form. The first term is the mutual information between your inputs X and the representation Z. This is this particular arrow. So you're trying to design a probability distribution for Z given X. Let us call it the encoder. It encodes data into the representation. And you want to forget stuff about the data, but of course you shouldn't forget everything about the data. That is what Alex said so beautifully in last week's talk. You want to make sure that this representation is good enough to make predictions on the target Y, right? So you would like to maximize the mutual information between Z and Y. And if you do a good job of maximizing this information, then you're learning a good classifier. And this particular part, so Z going to Y, is really the classifier. So if you imagine this as a large neural network, think of the first arrow as the first few layers, the second arrow as the last few layers of the network. Okay. And this is what is called the information bottleneck. It is a bottleneck because it takes in all the information in X and throws away everything that is not relevant to Y, and calls the result Z. Now there's a big problem with this, right? So the information bottleneck Lagrangian has been studied a lot over the years because it is quite fundamental in many fields. But I give you a source task, frequently occurring images. I would like you to solve a new task, strawberries. If you throw away all the information from the frequently occurring images, then you're really not going to do well on strawberries, because everything that you throw away is the stuff that you need for classifying strawberries. Everything that you keep is the stuff that you need to classify the frequently occurring images. So if you design a representation that is minimal or that is small in size for the source task, it necessarily involves throwing away everything that the source doesn't need. If strawberries are essentially as good as the source task, then well, you are not really doing any transfer learning. And if they're different, you already threw away all the information from the source task. So you might as well not have had the source task. And this is quite an important point, right? We like to think of the information bottleneck as formalizing all representation learning, but clearly neural networks learn transferable representations. Your brain also learns very transferable representations, plastic ones. But this principle does not let you understand them. Fundamentally, it says that you cannot have transferable representations unless the two tasks are essentially the same. So here is one way to fix it. You would like to modify the information bottleneck to have other terms that maintains some amount of redundant information from the source task. Why redundant? Because it is not necessary to, it is not relevant to classifying the source, but it is relevant to classifying the target. Now, of course, the best redundant information you can retain is if I give you the target to begin with. If I give you the strawberries, then you will simply learn a classifier that is good enough for strawberries. But you don't know that. You would like to, the entire purpose of transfer is to pre-train in such a way that you can transfer to many different tasks. So you pick some blanket all tasks. So this is what is called, we call it a canonical task. And one example of a great canonical task is simply reconstruction. So in addition to having your classifier predict the labels, you also have your representation predict the input itself. And this forces it to become an autoencoder. This forces it to measure, to retain everything about X, even if that is not relevant to classifying Y. Okay. And here is how the model would look. So this is your standard neural network, the encoder of first few layers, the classifier, the next few layers, and then secretly you tap off a decoder, which tries to measure how good these features are for reconstructing the input itself. Okay. These are quantities that Alex alluded to last time. But here is how you would write them down. So distortion D measures how well your representation works for reconstructing X. So if you take a JPEG image, JPEG is a lossy compression. So you will have some error between the original image X and the JPEG image, the mean square error of your JPEG image. And that is essentially distortion. It measures how likely the input datum is under your representation Z, averaged over all possible representations Z that you could have cooked up from your representation, from your input image X, the overall encoders. The rate measures the size of your encoding. So ignore the denominator. The denominator is also something that Alex mentioned, but let's say it is just uniform for now. And this is really the entropy of your encoding distribution. Larger the entropy, more the information that you're retaining about X. Smaller the entropy, worse the more the redundancy, or more you're forgetting about X. Okay, and this is what is called the rate in information theory. It is an upper bound on the mutual information in the first term of the information bottleneck, X and Z. Let us look at this picture. It is traditional in information theory to draw pictures like this, rate on the x-axis, distortion on the y-axis. This is exactly the same picture that Alex showed in his talk. I have stolen it from one of his papers, in fact. The red curve is the curve of all representations that have maximum entropy for so-and-so rate and for so-and-so distortion. So everything to the right of the red curve is stuff that you can build. Everything to the bottom of the, below the red curve is stuff that you cannot build. If you take the size of your neural network that is parameterizing this probability distributions, let the W here to infinity. So you are picking, if you pick really, really large neural networks, then this curve, which is a convex curve, you can show this easily, hugs the axis, okay? And the parameter lambda that defines how much you focus on rate versus how much you focus on distortion lets you control which part of this red curve you belong. So you should really imagine the training process as starting somewhere here, and depending on what lambda you pick, converging to one of these points on this surface. If I pick a lambda that is very, very large, then I'm forcing the representation to really focus on distortion while ignoring the rate. So you will get a huge amount of memorization going on in the encoder, but obviously you will get a low distortion, and vice versa for this side of the line. Now, in practice, you will often see people training very, very large neural networks using variation inference because the libraries are very good at doing this. But what happens is as this curve starts hugging the axis, you get a huge locus of solution. So this is an entire locus of lambda equal to 0. This is an entire locus of lambda equal to infinity. Those are the trivial ones. You would never use them in practice. But lambda equal to 1 is something that you always do in practice. So essentially, all of the empirical variation inference literature would set lambda to be 1. This is the famous elbow, in fact, just written in a different notation. And the important thing to notice is that this Lagrange multiplier does not let you control which part of this particular line you lie on. If you lie on this point, depending on the initializations of your weight, you will learn a representation where the rate is minimal and the distortion is 0. This really means that the decoder has completely overfitted and the representation is completely trivial. It is not retaining any information about the input, and yet the decoder is getting perfect reconstruction because the decoder is memorizing all your inputs. If you lie on the opposite point, the opposite thing happens. You will have very low distortion and 0 rate. Okay. So it's very important to understand that these functionals come with certain caveats in how you use them for very large variational families like neural networks. Variation inference is fundamentally not about using large models. It is about using small models to approximate large probability distributions. Neural networks make it very easy to forget this, but it will hurt in practice. What we are going to talk about is a slightly different functional that Alex discussed towards the end of his talk. This is the rate, this is the distortion, and now we pop in our classifier. The classifier is the third branch of the neural network. It measures how well you're doing for predicting classes Y, averaged again over all the latents of your encoder. Okay, and we would like to understand how the rate distortion curve looks like. This two-dimensional space, one-dimensional curve looks like for these 3 players now. And here is how it looks like. So I'm going to plot in 3 axes now: rate, distortion, and classification. And you can again prove that this is a convex surface, the surface of all possible representations you can learn that are maximum entropy, give for so-and-so rate, so-and-so distortion, and so-and-so classification. Okay. And as I said, training should be really thought about as beginning somewhere outside this surface and then converging to a particular point on the surface, depending on what lambda and gamma you pick as the Lagrange multipliers of D and C. And you can show this quite beautifully. So just like free energy is minimized when you run a stochastic processor or any Markov chain, for instance, this equilibrium surface, we like to call it an equilibrium surface. It consists of the minimal free energy, this particular minimal free energy for a particular lambda and a particular gamma. As was also said last week, thermodynamics fundamentally is nothing more than saying that this surface is continuous and differentiable. So given any point, you can go around that point with with 4 tiny steps, and you will get conditions of this kind. So these are the KKT conditions for the surface. If I let you have a little bit extra rate in your code, if I let you remember a little more about your input, then well, you will reduce the distortion a tiny bit, or you could also reduce the classification a tiny bit. Let's not worry about the entropy. And that is how you would use the extra bits that you have at your disposal to either improve performance on reconstruction or improve performance on classification. And there is a trade-off in other directions also exactly of this kind. And just like in a thermodynamic system, you would conserve physical energy. In this system, we have concocted a model where information is conserved. So the input has some information, either it lives in the encoder decoder pair, or it lives in the encoder classifier pair. once you have a surface like this, you can kind of cook up processes that travel on this surface. So this line of thinking began when Alex was telling me about his paper, I think in the ICML of 2018 in Stockholm. And he said, oh, look, Pratik, I have this very nice surface. It looks very interesting. Can you design ways to explore the far off points of this surface? And it seems quite daunting because the far off points may lie very far away. But that is how we began looking at this surface. You want to design processes, the stochastic processes that travel on the surface. To what end we'll find out. So let's think of an quasi-static process. A quasi-static process is stuff that remains on the equilibrium surface always. So you're always in equilibrium. And you may want to have certain other constraints imposed upon the process. So d by dt of your some functional of your the gradient of this function with respect to weights, if it is 0, this tells you that your parameters are forced to remain on the equilibrium surface. And you can have any which other constraint. Here we are using what is called the isoclassification condition, where you say that change my weights in such a way that you don't change the classification loss. So you're allowed to trade off rate and distortion to whatever end you want, but do not change my classification. Essentially, this boils down to slicing this manifold along a line at constant classification, obtaining this particular curve, and then being able to travel up and down this curve using lambda. And you can do the same exercise for any of the other axes, but this is kind of the one that we did. As I said, you can travel up and down the rate distortion curve for a given classification. So the classification loss is what I'm plotting here for CIFAR 10. It is essentially constant as you keep modifying your Lagrange multipliers. But here is a beautiful thing that you can do now that you have the surface from Alan's work. The surface fundamentally is not a function of how you train and etc. It is only a function of the data set that you're using to train and the model that you are using to train the variational family. So no one is stopping you from changing the data set now. So what we're going to do is take a source task, PS, take a target task that you want to transfer to, and design some trajectory in task space. Here we are simply doing a mixture model of the two distributions. So T is a parameter that goes from 0 to 1. If it is 0, you're at the source task. If it is 1, you're at the target task. And this is an interpolating task. You can come up with more intricate ways of interpolating tasks, which is what we've done in some of the later papers using, let's say, Wasserstein geodesics. But fundamentally, it is about drawing a trajectory in task space, task meaning simply a joint distribution of inputs and outputs from the source to the target. You should imagine this as the equilibrium surface moving from the source of whatever location it is at for the source to the target. And while the surface moves, you would like to keep the parameters on the surface. Why? Because once you found the surface, you are done with training, right? You don't want to forget it. The outside the surface lies misery, so all the non-equilibriumness of the process. On the surface, you know that you are at the optimal representation. So here is how an isoclassification transfer process looks like. You modify the task using any trajectory of this form. You force your isoclassification process to execute. So this way, this forces the weights to evolve in such a way that it tracks this particular task. And as T goes to 1, you move the weights to become good for the target task. The beauty of processes like this is that dc by dt is 0. So if you have 95% accuracy on the source task, if your variational family is large enough to give you 95% accuracy on the target task, and we'll see why this may not always be the case later, but if it is good enough, then this process will find that weight vector. This is totally unlike anything that you would see in the literature today. So the most prominent way of transferring representations is to fine tune. You pre-train a model, fine tune on the target, and if you don't like the result you get, there is really nothing you can do about it. You try different hyperparameters, you try different network, etc., and there is really no understanding that you glean from those experiments that tells you how to get better results from transfer. This is a completely controllable way of transferring representations, and it's very abstract. So it's not terribly easy to implement these things in practice at scale. We are still working on it, but formally speaking, it lets you do completely control the target task's error. Here is how the process looks. So the blue line is what we call the non-equilibrium process. This is exactly fine tuning, and it is showing you the accuracy on the target task. So in CIFAR 10, there is 4 vehicles and 6 animals. So you are training a model on vehicles, transferring it to animals, and obviously the error of the model at the beginning of fine tuning is very high on animals, and as you train, it improves. Let's say about 80% accuracy. This is the ISO classification process. It starts off with a high error because this particular point was calculated for vehicles. It is the interpolated task at equal to 0. So every point on the orange line is a different interpolating task, but the final point is animals. In between, you are really training on a mixture of the source and the target tasks. And while it is not exactly constant in the experiment, it is roughly constant. The green across is what you would get without any transfer. So if you directly were to train the same model on animals. And of course, the non-equilibrium process, this is where you see some of the difficulties of living outside the surface. Ideally, you want the blue line to be at least as good as the green cross, but that may not always be the case in practice. We are already at 47 minutes, but how should we do this? So
I think, do you have a code walkthrough? I forget now.
I have a code walkthrough, yes. I have about 10 to 15 minutes of code walkthrough. So here is what I will do.
So what we need to do is just at least see if there are quick questions. So we have a short break and then get back to it, right? Because that will give us an idea of how much time we will have.
Mm-hmm.
So if people have quick questions on what Pratik has presented so far, you can type it in the Q&A or raise your hand.
Maybe I'll kick off with one quick, maybe from your perspective, or maybe a minor quibble from my perspective as a thermodynamicist, right? Time is not traditionally a variable in thermodynamics, right? So actually, the way I re-modified your slides when I presented in my stat thermo class is you can state that ISO classification condition as C equals C naught, right? Which is the same as preparing an ensemble at constant volume, for example, right? Which is actually the point you made in one of your talks around thinking about the ISO classification process, for example, as like a isochoric process, right? Where we hold the volume to be constant. So I'm just curious if we could just as easily just say it as C equals C naught, right? Where you're setting it to be some constant number, right? And reformulate the whole thing, which of course then will give you the same condition. But I think I guess, I don't know if this is just a quibble or maybe there's some conceptual difference in that style of thinking.
Let me let me try to explain. So the way I wrote it doesn't actually distinguish this, but there are 2 times here. There is the time of the stochastic process reaching your equilibrium, which is you falling down on the surface. That is asymptotic, so that time goes to infinity. But this time, it might as well be S. So this is a totally different time where I am now changing the system itself. And yes, so you can create an ensemble and write C equal to C naught while your system evolves. And it is, and so you're really like taking a process which you imagine as having reached equilibrium, modifying the systems, and then reaching some other equilibrium point of a slightly different system now. So you're right in modifying the notation to say C equal to C naught for all times after the first equilibrium was reached.
Yeah. Okay. I think that makes sense actually. I mean, what you're essentially saying is that C equals C naught along a path along a path that you would like to take the system. You would like the system
of the isopodic process.
Yeah. So you're essentially moving in this RD, I guess RDC, or in this case RDC or RDS ensemble, and with fixed C. So obviously you're changing the rate and the distortion,
yes,
while you're keeping C fixed, right? So which is, in a sense, right? I mean, it's exactly the same as what we do, right? In a thermodynamic ensemble where I keep volume constant and then change. Let's say if I was in a microcanonical ensemble, I'd change the number of particles and the energy of the system. So I think in that sense, it's actually almost one-to-one mapping from that style of thinking to what you're presenting.
Yeah. What I don't understand too well yet is these processes are very slow. In practice, you're never really implementing the equilibrium process itself, because it is horrendously slow to travel on the equilibrium surface. So what we do in practice is we kind of hop on it. So you increase the temperature a little bit, bring it back down so that you don't lose the surface, but you still get to speed up a little bit.
Which is also true in thermodynamics, right? If you try to traverse the equilibrium path with like a standard Metropolis Monte Carlo, right? You move very slowly, right? Which is why you do all this sort of Hamiltonian Monte Carlo and so on, where you give the boost momentum exactly in this sort of same way, right?
In HMC and stuff, the ensemble is a little simpler. In here, there is RDC playing. It's pretty complicated to run HMC style things, and we've tried it because every functional here is an integral over Z. So you need to spend a lot of work computing. It's not. Conceptually it is easy, but computationally running HMC style algorithms was pretty difficult for this. So we do this like temperature annealing.
Yep. So Venkat, your question was answered?
Yeah, no, I'm super happy.
All right. So there's another question in the Q&A, and the question is from Victor Venturi. So from my understanding, the transferring from source to target is done by evaluating the new optimal surface as a function of new training data. Is that correct? If so, okay, is that correct?
Yeah.
All right. If so, how would you do something similar, but instead of only evaluating changes in the equilibrium surface based on data, could you also incorporate the possibility of changing the model? I think that's a very interesting question.
Yeah, that's a very good question. Variational families are funny, especially for universal approximators. The equilibrium surface of a smaller model lies above this equilibrium surface. Let's look at this curve. So all models with fewer weights, for instance, will have an RD curve above this curve. All models with larger weights will have an RD curve below this curve. Now, there are ways of modifying the model at runtime. You add a few neurons to your layers, so you make it a little wider. that will give you a better variational family. So in principle, you can do it. I don't know how, what for, because this particular curve, even for like fairly small neural networks, is pretty close to the axis. In fact, if you see this and you are keen-eyed, you will see that this rate distortion curve looks like a straight line. So you are actually hugging the axis somewhere. So you're already in the problematic regime or close to the problematic regime anyway. So you have to be very careful in changing the model, and there are ways. So you will see a lot of work, not for these kinds of problems explicitly, but where people try to add a little more capacity to the learner while doing continual learning, freeze existing capacity in continual learning. I would have showed you some slides on it later, but roughly speaking, I think it's a very good idea, but I haven't tried it.
Yeah, thanks. And when you change the model, you're not guaranteed to stay on that convex surface, right? Because
no, yeah. So you have to keep training the model. Yeah.
Yeah. Right.
Yeah. So you have to keep training the model and try to kind of because every time you do SGD updates, you are going closer to the surface of whichever model you have at that instant.
Yeah. Right. So I think that was a quick break, but I think we can continue and manage time as we move along.
Okay. So here is how I will do this. I see it is 56 minutes past. I will show 2 results in about 5 minutes. Then we'll do 15 minutes or so of code walkthrough, or my style of code walkthrough. And so here is one. So we made a big deal of how this process can transfer from anything to anything, but clearly that's not true, right? You can take a model that was trained on cars and cats, and it's not very easy to transfer this model to images, to MRI images. So while in principle you can, the mathematics does not prevent you. In practice, it is difficult. And we would like to understand why. So there's clearly instances when transfer learning fails. You can imagine intuitively that if 2 tasks are close to each other, if both of them are RGB images of natural objects, transfer could be easy. Transferring between flowers and dogs is easy, but between flowers and MRI images is difficult. But you don't really know what close means in the space of tasks. And there are many ways of constructing such distances, but none of them is canonical. So you can never claim that a metric is unique, but we don't even know what the metric is for a lot of the methods. Typically in practice, people will simply try to fine-tune a model from one task to the other and say that if fine-tuning was particularly difficult, then the target task was far away. And there is merit to this, and I would say this is the best way we know today of checking distances between classes. We don't really know anything more than or for instance, we don't know how to do fine-tuning in a bulletproof fashion, but using fine-tuning to measure distances between tasks is actually a pretty good way to do it in practice. So here is what I would like to do. I would like to construct a way to measure distance between tasks that understands the fact that you are fitting a neural network. So a task is a joint distribution between inputs and labels, and you can think of scale divergence as being one distance, but that doesn't understand what hypothesis space you are using to fit the task. You can imagine that if you fit a larger model, which could have fitted both the tasks in one go, then the distance between them is 0. If you fit a small model, then the distance between them should obviously be large because it takes you some time to travel the entire trajectory for the small model. And we would like the distance to have these kinds of features, which you won't see in a lot of other ways to measure task distances. And the second one I already said before, you want some theory that guides this rather than just fine tuning, for instance. And here is the method in a nutshell. We would like to think of classifiers in this case as the probability distribution of tasks, the labels given inputs X. These are the weights of your model that you trained on your source data in whichever way you will. Let's say that I give you a target task. A target task consists of a distribution on the inputs from some new categories and their corresponding labels. And you don't really know what weights you will use for the target task. But let us imagine that someone told you what the weights are. You would like to find the shortest trajectory between these weights, WS, and these weights, WT. There is very good ways of measuring distances between in the weight space. The most interesting one is what is called the Fisher-Rao distance. The Fisher-Rao distance is the distance that is invariant to reparameterization of the model. So if I pick a slightly different neural network to express the same probability distribution, a different neural architecture, the length of the trajectory should obviously not change because this is a trajectory in the space of distributions. And Fisher-Rao distance will give you ways of measuring such distances. It is the integral of the incremental KL divergence along this path. Okay, so we know how to move, given one input X, you know how to measure distances in weight space. But of course, your inputs of cars in this data set are very different from the strawberries in the target data set. So you would also like to move the task in some nice way. In the previous few minutes, we were just constructing a mixture distribution of the two tasks. In this case, we are interested in optimally moving the task from the source to the target. As we said, you can use, let's say, Wasserstein distance to move them, but the Wasserstein distance, again, does not really care about what the classifier is, right? So you want to move the task from source to target in such a way that the weights can follow this task, and you want the length of the trajectory on the weight space to tell you how easy it is to take one input here and move it to some other input on the targets. So you should think of measuring or this way to measure the distance between tasks as a synchronized transfer of the weights and the task. And the synchronous feature, the synchronous nature is very important here, because if you directly start training your weights on the target task, which is what we do in fine tuning, then the weights have to kind of fight to catch up, right? So they may end up taking a large trajectory in the weight space. If you don't have the way you evolve the task depend on the weights, then you are not really doing anything in terms of computing an optimal transfer distance. You are modifying the task in some way and your weights will track it. So you will get something like the ISO classification process. And in the last few slides, this is not a distance, it is simply a way to transfer. What we want is an optimal distance. And in a recent paper, we constructed an algorithm to measure and compute such distances. And mathematically speaking, we can claim to compute the information theoretically optimal distance between two learning tasks. I will not go through the details, but here is how it looks. So this is a little cryptic, but it's actually quite easy to understand. Let's do the second line first. The second line is simply stochastic gradient descent on the interpolated task. These are the weights that are at time instant tau. P tau is the interpolated task between the source and the target. The interpolation is occurring through optimal transport, but the cost of optimal transport is actually coming from something called as McCann's displacement in optimal transport. It is a way to take two tasks and compute some interpolation between them. And this is simply the length of the trajectory in information space, the incremental, the square root of the KL divergence integrated over the entire trajectory of the weight space. If you can compute this, then you know that this is the information theoretically optimal transfer distance. And let me give you one example of this. So remember we said if the network is small, we like the distance to be large. If the network is large, then we want the distance to be small. And here is one example that shows this. So these are 5 different classes tasks from CIFAR 100. So each of them has 5 classes. And you can compute the distance that we just talked about for, let's say, a small convolutional network. And roughly speaking, for these 5x5 matrix, all the tasks are close to each other. There is not that much distance between the tasks. And this is something that fine-tuning does not give you. So if you look at fine-tuning distances between the same 5x5 tasks, some of them you'll be able to fine-tune trivially, some others may conk off and never work. And this is what a practitioner lives with every day today. But the real distance between these tasks actually looks like this. All of them are close to each other if only you knew how to transfer nicely. And fine-tuning is not the nicest way to transfer. Okay. If you run the same experiment with a larger neural network, then every single number in this matrix is smaller than the corresponding number in this matrix. That tells you that larger the network, smaller the trajectory that you need that you need to travel in information space to transfer. So this gives you 2 things. It gives you a distance between tasks that is canonical in some way. It is the information theoretically of smallest distance. And it also gives you a way to transfer. The way to transfer is not very practical yet, but it is the optimal way to transfer. Okay, so that was about distances between tasks. Can you always do this? Well, not really. So there are tasks that are synergistic. There are tasks that are not synergistic. So you will always see in practice that and just because you have a large number of tasks doesn't mean that you do well on them always. And there is different ways of understanding this. Here is one. So classical results in learning theory will argue the following. So they'll say that if you have data from m tasks, if you give me n samples from every task, so you give me m times n samples in total, then I wish to minimize the average population risk on all these m tasks. This is a complete parallel of VC dimension bounds for standard supervised learning of one task, except that you're doing stuff for multiple tasks. And this is kind of what Jonathan Baxter did in the late 90s. The number of tasks that you need goes down as roughly 1 over epsilon squared. That is a standard VC term. But this particular term is something that is smaller than the VC dimension. And that tells you that if this term, which really expresses how many samples you have, how related the tasks are, etc. If the tasks are related, then you don't need too many tasks to do well on every task. And roughly speaking, this theory says that if you want to minimize the average population risk on all tasks, then more the tasks, the better. But that's not really true always. So you can also identify tasks that compete with each other. After all, when you do multitask learning, you don't really care for the average accuracy on all tasks. What you care about more is the accuracy on one particular task. So pick my favorite task. This is what I would like to do well on. And everything else is just a way to reduce the sample complexity for such tasks.
Just a quick time check. How much longer is your talk?
Yes, I'll do maybe 2 more minutes of this.
Okay, you don't have to shut down that soon, but I just wanted to remind you.
No, that is the plan. Yeah.
All right.
So so we have a theorem that essentially express the idea that if you have a fixed hypothesis space and you try to pump in diverse tasks in the same hypothesis space, you're not going to do well on all tasks. And that is what we call task competition. It is very non-trivial to understand this competition. So here is an experiment. It is again CIFAR 100. And what we are doing now is focus on, let's say, one of these tasks. So man-made outdoor objects. this is one task, and we're going to train it with many different tasks. So x-axis consists of many different tasks. There are 20 possible tasks you can train with. So this number would have, or let's say this number is when man-made outdoor is trained with 10 other tasks. So there are 11 tasks in total, and you'll get so and so accuracy on it. If you add a 12th task, your accuracy drops on man-made outdoor. If you add a 13th task, it again comes back up. If you add a 14th task, it again goes back up even further. So it's completely non-trivial which tasks you want to add if you want to do well on man-made outdoor. And this is true for all the other tasks also. So, and we have ways of characterizing which tasks help and which tasks do not help. And training only selectively on tasks that do help. So I will only briefly mention this. So this is a recent paper called Model Zoo. It is essentially runs AdaBoost, the boosting algorithm AdaBoost on tasks. Just like boosting takes your samples and then splits them, fits weak learners on subsets of samples. This method fits models on subsets of tasks. The idea being that if you train on synergistic tasks, then your model one will be good. And at the later, you can always ensemble these models and do well on all tasks in one go. I don't want to go through this here. But the moral of the story is we want to understand why transfer works well. Or why multiple tasks are so useful to train together. Things like the RDC surface that Alex talked about that we kind of try to extend are ways of understanding representations. There are ways of understanding when representations are plastic, when they are more discriminative for your particular task, etc. And they can give you like an entire one functional that lets you understand everything that is to do about about representation learning. We have been exploring the space of tasks using functionals like this. So these days we are playing a lot with S, RDC, and S in a way to understand better how many representations work well for the same task. I will stop here and you can read more in these papers. Are there any questions before we begin?
Yeah, let's maybe spend a minute or two or a few minutes. So while people are formulating the questions, I have a quick one. So a lot of what everything that you showed has a classification task at hand. But if we look at the regression side of things, do you have any specific things to add?
We haven't played too much with regression, and I don't think it will change fundamentally any of these functionals. Yeah, I think that is the short answer.
Okay.
We haven't tried it, but I don't think it will be different.
Okay. Fundamentally, you are playing in a continuous infinite dimensional space, right? So that's.
I didn't catch that. Sorry, what?
I said, so many of the regression problems tend to be in the infinite dimensional space. So that it's continuous domain problems, right? So they tend to be a little more, I would say theoretically similar, but practically implementation wise.
Yeah, so we have some papers where we do regression on tabular data, not multitask regression.
Okay.
But really, like there is a very, very powerful techniques. One of them, let's say, is called stacking or ensembling. Yes, the regression problem seems more difficult because you want to predict a real number, but it has also been much better studied. So we have very powerful ways of answering those questions.
Okay. Yep. Thanks. All right. So maybe we can jump directly into the code walkthrough and then use the remaining time for discussion.
Yeah. So I'm going to do a slightly different kind of code walkthrough. and I call it the dirty laundry of deep learning. So this is all the stuff that you don't see in these kinds of talks. And this is my wisdom from the last few years. You can use it to whatever extent you like it. But here is some. So even fine tuning, which essentially people would consider trivial, has a large number of secret sauce tricks. To go back to the few shot learning experiment, this is how the algorithm looked. So you train a large deep network on a meta training set with a standard classification loss. Now, how large is large, or how large is your meta training set? We were training on meta training sets with thousands of classes. So there was about 7,800 classes in the ImageNet 21 experiment. And there are a bunch of tricks that you would do when you work with those problems as compared to the MNIST sensor files. Okay, and we'll talk about it in a bit. Let's say you finish your pre-training. Now you would like to do fine tuning. Now, the standard way to do fine tuning is that you rip off the last layer of the classifier and plug in a new classifier head, and use that to classify your new images, your new classes. Now, this is not really the best way to do things. So you can cook up a few more practical tricks to do it. We'll talk about this. Yeah, so let's look at the first one, the how to select a classifier. This is what is called support-based initialization. In the metric learning literature, it also goes under the name of imprinting. And here is how it would look. So let's say that I have a pre-trained model, let us call with parameters theta. So, and this is the logits of my pre-trained model, z theta for input x. I would like to add a new classifier layer to this model. And I'm being very particular about calling z the logits of the old model. And you will see why in a bit. So roughly speaking, we want to add a new fully connected network layer. W are its weights, B are its biases, sigma is the nonlinearity, let's say it's a ReLU that gets applied to your old logits to get your new logits. Now, these new logits are going to be trained using the cross entropy loss. And if you write down the cross entropy loss for this larger model, W comma theta, you will see terms that look essentially like cosine similarity. So up to the normalization that comes from softmax. But if you wanted to do well on new images from different classes, if you can initialize this weight vector W to always have a large inner product with the right classes, right images, then you would have initialized it in the best way. There's no need to initialize W randomly. We know a little bit about what it is going to do. And here is one trick. So you take in an image of class Y, feed it through the network, look at its features. These are its nonlinearity applied features, and simply normalize them and set the particular row of W to exactly that normalized vector. When such a vector hits your representation, you get a much larger inner product with the correct class Y as compared to any other class Y. And this is the difference between fine-tuning in one epoch versus fine-tuning in 20 epochs, especially for very large models. And here is another trick that you can see from this. So remember that I said that Z are the logits of my old model. Now, when you're transfer learning between, especially for few shot learning, when you're transferring from a huge model to a very few number of classes. So I meta trained on 7,000 classes and I want to classify 5 new classes. There is really no need to throw away the last classifier layer. You can plug in a new classifier layer on top of the 1,000 logits, and that is still good enough because these 1,000 logit space is still a good representation for all your inputs. It is the identity of the classes, and you're taking the identities of the old classes, 7,000 classes, and then creating a new feature vector out of it. Okay. And this will again save a lot of sample complexity for the few shot case. Here is one that is a little more commonly known called label smoothing. The cross entropy loss is fundamentally very ill conditioned. So the correct logic is expected to go to positive infinity if you want to go get zero error, zero loss. And the incorrect logics are expected to go to negative infinity. And then you get this big fight now in when you train very large multi-class models, because one correct logic is going to drive down the values of all the other logics if there are lots of. Label smoothing is a trick that essentially uses not a one hot vector itself, but a 1 minus epsilon hot vector. So it pulls off some epsilon mass from your true class and gives off that mass equally to all the other classes. So this is no longer one hot. And you can do some very basic derivative to show that the logic that maximizes the cross entropy loss with label smoothing does not go all the way till infinity, it saturates. Whereas if you did not use cell label smoothing, it will saturate. This is a very useful trick to use for large problems. It also works fairly fine at the CIFAR 10 level, but certainly at CIFAR 100 style problems, you will find it very useful. A big thing that is becoming very apparent in the literature is that the benchmarks that we fight for 0.5% on are actually not that nice. A lot of benchmarks, including ImageNet, including CIFAR, will have 3 to 5% incorrect labels. So every number you see in the paper, you should imagine it with an error bar of 3 to 5%. Even for very, very widely used datasets like CIFAR 10, a few months ago, people noticed that there were some images that were repeated between the training set and the validation set. So there were not too many of them, but there are big bugs in the data sets that we use. For very large ones like ImageNet 21K, the annotations themselves are quite incorrect for many, many images. And that is what makes it challenging to go to scale, where you cannot really look at the entire data set. How to choose hyperparameters. This is something that is very daunting, but here is my perspective on this. So hyperparameters are name of the game. So there is really no way to cheat around them. But the better engineer you are, and this is what I mean by being a better engineer. So when we build complex systems, just like a mechanical engineer, or I was trained in aerodynamics, we are fans of non-dimensionalizing everything that we ever use in undergraduate textbooks. So aeronautics really looks like this gigantically messy field where no quantity that you write down is actually something that you will measure using one experiment. You need 3 experiments to measure it. But the moral of that story is that there are very complicated things you build with neural networks. The more careful you are in making sure that if you have a regularizer and a loss, the regularizer and the loss are at the same scale. If they're at different scales, then you need to make sure that you can bring them back to the same scale. The better job you do of it here, the easier job you will have of picking hyperparameters. And many instances where people say it's very difficult to pick hyperparameters, they're really like not being very careful in how they set up the problem to begin with. But let's say you did this and you're still in a fix as to what hyperparameters to pick. There are certain thumb rules. So for instance, optimization hyperparameters are essentially a done deal at this point of time. And here is how you would pick them. Learning rate, let's call it eta, the batch size is B. Let's say your Nesterov momentum is a rho, and this is the weight decay that you have in your model. So it turns out that this particular quantity, learning rate times the weight decay divided by batch size divided by 1 minus rho, is an invariant. It's an invariant that keeps the stochasticity of stochastic gradient descent constant, the noise in SGD constant. And this invariant is going to completely tie 3 parameters, and you will be only left with picking one, typically the learning rate. So this has been noticed many times in the literature. We had batch size and learning rate in this paper. Smith did batch size, learning rate, and momentum. This one is the CEO of Myrtle.ai. So he, I forget his name, but he had the series of blog posts where he discovered that you can add weight decay on the numerator and even remove that parameter from the training. So let me actually do the following. So if you see my screen, this is the, oops. This is a company called Myrtle.ai, and they have some nice blog posts that you can follow. Very deep and intricate blog posts on basics of training. Fast AI is a library that essentially is a wrapper around PyTorch. It has implemented a bunch of nice functionality to pick hyperparameters. One of my favorite ones is called how can yeah. So one of my favorite ones is called Learning Rate Finder. And it is a mechanism where you play the following game. So you start training your model and you increase the learning rate after every mini batch that goes through the network. As you start increasing the learning rate to very large values, you will see that the network starts training from very small learning rates to very large learning rates. But at some point of time, you are going to pick a large learning rate. So the learning rate should be 1 over the smoothness, 1 over the ellipsis constant if you're doing convex optimization. And once you go beyond such upper bounds, your loss will no longer go down with successive mini batches. And roughly speaking, an area somewhere, a point somewhere here is a good way to pick a learning rate to train models with. And this is a very robust way to select learning rates that essentially completely eliminates even learning rate from the game. It was discovered by this researcher in Naval Research Laboratories called Leslie Smith, who also has a very interesting suite of techniques that go under the name of one cycle learning rate. And I happen to be a very big fan of this. So picking the right learning rate is quite critical to regularization, but it doesn't have to be critical to training. And here is, or it doesn't have to be critical if you follow this. Let's say if you're training for 400 iterations.
Can you like make that bigger, like page width or something so people can see? Thank you. A little bigger if possible. Yeah, better.
Yeah. So let's say, let's say you're training for 400 epochs. A good learning rate schedule to use is something that goes up in about 10 to 15% of the training, essentially as quickly as it can, linearly, let's say, and then comes down as slowly as it can. Typically, people like to use a cosine schedule. And there are good ways that suggest this, even from theory. You don't want to use staircase-based schedules because the temperature of staircase-based schedules is not is very difficult to determine. And what a cosine learning rule gives you is that it allows the system to remain at a specific temperature for essentially as long as it needs until it finds a nice entropic barrier to escape in a high dimensional energy landscape. So moral of the story, learning rates that look like some kind of cycle like this are going to essentially eliminate learning rate from the hyperparameters. And now you are done with optimization specific hyperparameters. For everything else, RayTune is our method of choice. This is a library that lets you pick different hyperparameters and search over them using bandit-based search. So for instance, let's say in this particular example, there are two parameters, alpha and beta, and you do whatever you do in the middle to compute some objective based on these two parameters. Ray allows you to pick alpha, let's say using a grid search with some bounds and discretization. You can pick, let's say, beta to be a categorical variable, and it is going to run the canonical product of this configuration, but run it in such a way that if one of the models starts training quickly, then that one gets few more cycles or few more mini batch updates, and the other ones hold on. So you don't have to do this from the outside. Ray.tune will automatically take care of checkpointing your models, loading them in, training them back up, etc., etc. And this is extremely powerful because in the modern deep learning research world, you really need to do hyperparameter tuning. 5 years ago for research, it was not that essential, but now it is unnecessary. And libraries like this are make it very easy to do hyperparameter search. Another favorite of mine is what is called weights and biases. This is a database where you can log training runs. So essentially, this is like TensorBoard, except that it lives on their infrastructure, not your laptop. But for some of the multitask learning experiments, we ran thousands of models. So this is code, and I've linked to it in the website. So this is just the hyperparameter tuning part of the code, which you can steal. But we have done thousands of experiments over the course of about a year. Now, making sure that you're systematically logging all these experiments is a very boring thing, but it is the difference between having a result and not having a result. So weights and biases is what we used for this particular project. It's a beautiful tool that gives you all the results from your experiments at a glance and makes it actually easy to do research and systematic to do research. The last one of this kind that I want to mention, and I want to emphasize this one, is that especially for the kind of work that I talked about, it is essential to be very critical of every hyperparameter you have. So a lot of the papers that we have written over on these topics, they use exactly one hyperparameter configuration for the entire paper. So 30, 40, 50 experiments running exactly with the same hyperparameter. And if you are doing well in this setting, then it really means that you have a result. Otherwise, there is no end to tweaking things here and there. And trying to eke out a little extra performance, but that is not the objective of writing these papers. It is to provide a proof of concept and show that if this proof of concept can be better than essentially everything out there, then maybe there is some merit to this idea. And if we want to do science in a more rigorous way in the age of deep learning, I think stuff like this is really essential. The second one is how to pick architectures. I have a few favorites. So this is one that is a very old paper at this point of time from 2014. It is all convolutional network without any max pooling. That is why it became popular. Why residual networks we found to be very good in all transfer problems. These days, for a lot of unstructured data regression, as Karthik said, it is very useful to use these models called transformers. They are essentially fancier variants of fully connected networks. But certain thumb rules exist. So deeper networks do not necessarily work better. So ResNets are typically not good at problems that that look like transfer. In fact, I like to say that the human brain, there is about 6 neurons that connect the retina to the IT. That is the area of your brain that understands vision after a few layers of visual cortexes. So the human brain is not that deep. It is obviously a very bad analogy because it is structured in a very, very different way than neural networks. But the point I would like to make is that if things are not working, adding a new layer is not going to solve it. They're not working for potentially different reasons. I'm personally a big fan of 16-bit training. This is a very trivial way to get up to 2x speed up in training. The new GPUs allow this. And I'm not a big fan of multi-GPU training because it is always a lot of trouble to implement it, especially if your idea itself is quite complicated. In the last few months, there was this very interesting bug that people discovered between NumPy and PyTorch working together. So the moral of the story of this dirty laundry code walkthrough is that there are certain ways to do systematic research. You do all of them, but the beauty of deep learning is that a lot of discoveries have been made by running seemingly absurd experiments. So you want to be systematic in how you explore ideas, but there is a certain bravado that you are that it's good to have when working with neural networks. They work for mysterious reasons still, and they do work. So I will end here.
Thank you very much. I think that was some advice from the School of Hard Knocks, and I appreciate it. In fact, a couple of my students are listening, and one of them pretty much went through everything that you just said. We're still going through it. So, all right, thank you. That was really interesting, thought-provoking, and also practically useful. So, could not have asked for a better talk. But I do want to see if, half the people dropped out, but they just did so at 12:30. But for those who remain, if there are questions, it's a good time to ask.
Maybe I'll ask one, Pratik, that's been, or maybe this might be a different way to frame Victor's question, but in thermal, we know that there are certain ensembles that are better at describing certain kinds of problems, right? So there's different kinds of processes, like you said, right? Isoclassification. There might be other, we obviously will not always do, constant volume process, for example, right? We may want to do constant pressure process and so on, where now it's no longer the variable, the extensive variable, but the Lagrange multiplier that you want to control, right? So I'm curious if you've, just what are your thoughts on controlling the Lagrange multiplier?
So we've been fooling around this theoretically for very different applications in neuroscience, where the Lagrange multiplier is something that you get to keep constant, understand how it evolves, etc. So let me try to say something that is very speculative. I was trying to imagine. So in neuroscience, there is a part of your brain called the LC that I don't even remember the full name for anymore, but it is responsible for inducing stress, anxiety, etc. And turns out this is also responsible for learning in the first place. So when you go out and hunt, you need to be open to other stimuli because there is a tiger who can come and eat you. But if you're in front of the same tiger, you don't want to be open to other stimuli, because then you get distracted and get eaten. So the body has this way of modulating the output of LC to give you both adaptability of the representation and learnability in the first place. Creating the representation and having it adapt. And one way that we've been trying to formalize it is by changing these Lagrange multipliers. When we implement these processes, we actually do play with the Lagrange multipliers explicitly. When you keep some constant and move the others, we don't know yet what happens in the world of learning. But this is like it's a very beautiful question. Yes, I don't know. And the Lagrange multiplier is a slope, right? So you get to find different parts of the slope. You get to say that the slope is constant along some directions, but the equilibrium surface actually looks very flat. So because the neural networks are essentially a dense mapping in the space of probability distributions, certainly universe approximators. So you do expect the slope to be flat. You do expect the surface to be flat.
Yeah.
So,
very fascinating. Yeah, I think it would be interesting if we could construct a iso Lagrange. I mean, there are now 3 Lagrange multipliers in the full formalism, right? So there's obviously lambda is maybe more well understood, but the other 2, I forget the sigma.
Gamma and sigma. So sigma is easy. So sigma is just the temperature of your learning process. In fact, some of my older work, it shows that if you try to train with R and D, then you get S for free, because you're using a stochastic process to train R and D. So sigma is just the learning rate divided by batch size, etc.
Yeah, so I had a question on convexity. So for the RD curve, it's very easy to show convexity and it's very standard.
Mm-hmm.
But when you have the other variables, so under what conditions can you prove convexity? And is there a formal proof?
There is a formal proof, yeah. So you just compute the Hessian, and I don't think there is any complicated technical condition under which convexity exists.
Okay. Yeah, it's interesting that, I mean, I have not seen it, but I've not read the paper.
Yeah, you just compute the Hessian of F with respect to RDC.
Okay. And it's true for LME's 4 variable case also?
Yeah.
Okay, interesting. Great. Other questions from the audience?
Maybe just seeing the time here, we can think of wrapping up here. So we like to wrap up by asking both the session chair and the speaker what their thoughts are looking forward in this field. So what maybe are the next innovations or the next important steps that would allow for this few-shot transfer learning, or or more generally what you think of the next steps are in combining information theory with scientific machine learning.
Yeah, so Pratik, you want to go ahead? You want to go first?
Yeah, sure. I mean, I started studying transfer because I was very curious about how well few-shot works. I think the way it is evolving in my head is tasks are something that we take for granted. We don't really know. We understand when tasks are different, but we don't really understand why machines would find them easy or hard or similar. Essentially what we believe is that the space of tasks is not as complicated as we would think. So once there is a reason why pre-training from ImageNet is the is the first thing you do in any CVPR paper today, because it is good enough to learn representations for all tasks that you could try to tackle. So we want to understand how complicated the space of task is, and we believe that, for instance, tasks that you can concoct from similar domains may not be that different after all. There is a reason why the brain is so easy, finds it so easy to transfer representations. There is a reason why domain adaptation works so nicely for neural networks. So maybe the tasks are essentially not that different. This is what I would like to understand.
Yeah, I think Pratik covered it well. So from my end, I have been thinking very deeply about how information theory can help us comprehend generalization, right? True generalization, where we, transfer to completely new distributions. And one area that I feel there is a very significant gap is in reliable bounds, right? So a lot of the bounds that exist for generalization error and any learning theory bounds tend to have give a lot of insight, but are not quantitative. There are things like order of this or that, in the equation. So getting better generalization error bounds is a first step, and also using information theory to design experiments, right? To set up, to basically also generate data from data sources, whether they be high fidelity simulations or experiments. I think that's one other area that I think we'll see a lot of activity over the next few years. So it's a couple of things on my mind.
Thank you so much for those perspectives. And Pratik, thank you so much for this talk. I think I learned a lot, especially as the follow-up to Alex Alemi's talk last week. I think you went a little bit more in detail like how this could actually enable few-shot learning, understanding this from this information theory point of view. For the few people who are left, we're looking forward to Shoyaida's talk next week. Please tune in then.
Thanks so much.
Thank you very much.
Bye, everyone.
Thank you, everyone. Yes. Yeah. Bye-bye.
Bye.
Bye.